Welcome to the video on relative velocity. So here we're going to be talking about a concept which you are familiar with, everyday examples of, but the physics of it in terms of how we calculate it may not be as familiar. So what is relative velocity anyway? Well, all motion is relative. That's a concept that's been around since Galileo in the 17th and 18th centuries, where this concept that your motion is relative to another stationary reference frame. So when we measure something, like for example, at the moment I'm standing here, I've got two cars, and it looks like the cars and me are stationary. Well, we are stationary in relation to each other. So if this room is the reference frame from which we're measuring, we are both stationary. However, if we say that we measure our motion compared to, let's say, the sun, well, because the Earth is constantly moving around its orbit around the sun, we are located on the Earth, and so therefore we are in motion in reference to the sun. So all motion is relative, right? You know this by when you catch the bus to school. You might be sitting there and you might be reading your physics textbook, and you are stationary. You talk to your friend next to you, you're both stationary. However, a person standing outside the bus on the side of the road as the bus goes past, to them that does the measurement, you are in motion. So all motion is relative, and that was a Galilean idea, and is fundamental to some of the underpinnings of relativity when we get into Einstein, because we have some slight differences there on how it's interpreted, and it has some massive ramifications, but more of that later. So what we're going to be looking at here is relative motion. So the first thing you can write down is all motion is relative. And it's relative to a stationary frame. Oh, we've got a bit of a dribble there. We'll change pens. Still running. There you go. Shows you this room is so hot it's making the ink run. So all motion is relative. Let's try this one. So when we measure the velocity of an object, we have to have a stationary frame of reference. And so the motion between these two frames, the frame that's doing the measuring and the frame that's in motion, is relative velocity. So when we go to do that, and that works well. It's working well so far. Let's try two more. All right, that's a lot better. So we have our velocity symbol there, and what we're going to do is we're going to put a little C here because we're talking about cars, and we're going to put an E for Earth. So what this means is that the velocity of the car is considered the object of interest, okay, and then this is the reference frame, okay, and for this example, with this car, for example, it is the Earth. So if I turn this on, it has a certain speed, and that speed of that car is measured in comparison to the reference frame. So the velocity of the car in relation to the Earth. Let's just say that speed of that particular car, all right, let's say it was going at 50 kilometers an hour. Okay, so that car is 50 kilometers an hour with reference to the Earth, as measured from a person standing on Earth as the car goes past, and I guess we can say it's going to go east. Okay, so 50 kilometers east, right? If we have another car, then let's say the velocity of that car is different. Slow and steady wins the race. So this one here, the velocity of this car, and we might call this car B, and the first one we'll call car A. Okay, and so the velocity of car B is, we're going to say, is 25 kilometers per hour. Just making these up to make the main point. So we have two of these objects, car A and car B. So what is the relative velocity between those two cars? Well, we have to remember that when we work this out, the relative velocity is equal to the velocity of the object of interest minus the velocity of the reference frame. So that's usually the Earth, right? So if we wanted to find out the velocity of, let's say, car A, which is the fast one, let's turn this on and turn the slow one on. Here we go. 1, 2, 3. Right, if we wanted to find out the velocity of car A compared to car B as measured from car B, we would write it like this. So we want to find the relative velocity of car A as measured from car B. And so what we need to do is we go the velocity of A with respect to Earth minus the velocity of B respect to Earth. Okay? And so what did we say here? Well, we said that the velocity of car A was 50 kilometers an hour. And the velocity of car B was 25 kilometers an hour. So that means if you are sitting in car B, right? Car B is the reference frame, and you were looking at car A, then to you, as measured from you sitting in this car would be going away from you towards the east at 25 kilometers an hour. So in a positive direction. 25 kilometers an hour. Okay, so what we've done here is we've set up this equation, and this equation is very important when it comes to looking at relative velocity. Okay, we always have the relative velocity between two objects, then the object relative to the Earth, and then the reference frame as measured to the Earth. Okay, let's do another example and see if we can make this a little bit clearer. Okay, now we're back at another example here. And we've got two cars again. We're going to be doing this problem a variety of different ways. So let's have a look at the first one. We've got two cars. The car behind is the fast car now, car A. It's traveling at 100 kilometers per hour in that direction there. I guess we can call it the positive direction. So if I set up some coordinate systems, and I say that's east and that's west. So it's traveling 100 kilometers east. And then it's got a car in front of it going a little bit slower, going 80 kilometers per east. And so what we want to do is let's find out the velocity of car A to car B, and then the velocity of B relative to A. So let's set up our equation as we had before. We said that the relative velocity, right, the relative velocity was equal to the velocity of the object that we're after, minus the velocity of the reference frame, right, of where the reference is doing, and most of the time it's Earth, but in this case here it's not going to be Earth because we're going to measure it from in the car. So that's the reference frame. So let's just rewrite that as the reference frame. So let's do the first one here. So if we look at the velocity of A as measured from B, then we have the velocity of A relative to the Earth minus the velocity of B relative to the Earth. Let's plug some numbers in and see. We'll just make ourselves a bit of room here. So the velocity of A relative to the Earth was 100 kilometers. Velocity of B relative to the Earth was 80 kilometers. 100 minus 80 is 20 kilometers per hour east. Now, does that make sense? Well, yes, it does. Think about it. If you have two cars, one car here, B, and this is A, and this is where you're doing your measurement from, the reference frame. This is the object of interest, A. So what's happening? Oops. So what's happening is the car's coming up like this because it's coming up faster because it's doing 100 kilometers versus 80 kilometers. So if you were sitting in this car, watching this car come towards you, it would look like it's traveling at 20 kilometers per hour in reference to where you're measuring it from in this car. So the relative velocity of car A as measured from car B is positive 20 kilometers per hour. Okay, so it's going to be coming along at 20 kilometers per hour. It's going to be passing you and then moving away from you into the positive direction east at 20 kilometers per hour. Okay, what about the other way? What about if we were to do the velocity of B relative to A? So that's the object of interest now, which is B, and the velocity is where we're getting the measurement done, which is going to be A. So the velocity of B is 80 minus the velocity of A, which is 100, which is minus 20 kilometers per hour east. So let's just think about that. Okay, so here's our scenario again. We've got the fast car behind A and the slower car in front. But this time you're going to be measuring it, you are in A. So as you're approaching this car, which is going at 80 kilometers an hour, you're doing 100. It's coming back towards you in the minus direction by 20 kilometers per hour. So from your perspective, this is positive for you, right? You're going that way, but this car looks like to you it's approaching you and going in the opposite direction by 20 kilometers per hour. So therefore we have a minus symbol. And then as you're looking away, it's moving away from you in the opposite direction at 20 kilometers per hour, and hence we have the minus 20. So that's relative velocity of car B as measured by car A. What about if the cars come together? Interesting question. We're going to look at that in the next video on relative velocity to make it more interesting. See you then.